Thank you very much, Plus, for the nice introduction. Hello, everyone. I'm happy to be here. I hope you see the presentation full screen. Yes?
Yes, looks good.
Yes. Okay, great. So today I'm going to mainly talk about how we use these future climate models, or let's say outputs of future climate models in our engineering analysis. The thing is, during last, let's say, 2 decades, there has been enormous enhancement in research works in climate change modeling, but still the transfer of knowledge and data towards engineering and application is a bit slow, and in engineering we are lagging a bit behind. So we have been active towards that direction, hopefully adding to the impact of the climate change modeling in real society works. So we use these future climate models to improve our designs for the future. So for the future, as you know, we want to increase sustainability, and we want to do, let's say, good things towards climate change adaptation and mitigation. But the thing is, in engineering design, there are, for example, let's look at buildings and energy systems. That has been mainly our focus. We have been investigating the performance of buildings and energy systems for future climate. But the thing is, when we look into this, for example, there are many other variables or components or parameters that are affecting our analysis. For example, we have people inside building, we have different appliances, we have outdoor comfort, we have, for example, different performance of buildings, different types of buildings, retrofitting of buildings, and then energy systems. So at the end, there are multiple variables at each part. So if we look into, let's say, what we do, we want to use climate modeling outputs and then put them in our engineering design and assessment of models, and then come with this climate change mitigation and adaptation scenarios. So, and there are multiple variables in the engineering models. And as we know, when we work with climate modeling, there are considerable challenges there. We have climate uncertainties, then we need to work with large data sets, and there are differences in the spatial and temporal resolutions that we need and that are shared from climate models. So it's not like that, okay, we get the future climate data and put it in our models. We need to work still with the data, and we need to develop suitable weather data sets and the methods for the analysis on assessment. So we have been quite busy with these things. So in this regard, we have developed several methods or let's say approaches for impact assessment of climate change on buildings and energy systems. We have developed some novel methods for statistical and uncertainty analysis. We have developed representative future weather scenarios for building and energy simulations, and also methods for energy system optimization. And we have generated, let's say, novel approaches for urban and microclimate simulations. So what we do is that we mainly get data from RCM, regional climate models. Then we work with the data, climate data, we synthesize them based on our needs, and then we apply those synthesized weather data sets in our engineering models. So here I shortly describe, for example, an approach that we have developed, and it has been, let's say, used by other scholars in the field. For example, if we look into future climate data sets, RCM data, we need, for example, to get data from 13 different climate scenarios with different GCNs, different RCPs. Then we need also to look into long-term periods, for example, 30 years. Then it will be, let's say, 30 years of 13 climate scenarios, then 390 years. And then our simulations are based on hourly temporal resolution. So you can imagine how heavy can be the simulations, and technically we cannot run heavy optimizations, for example, for the energy system using these datasets. Then we have developed methods, for example, to generate representative weather datasets. This is like, for example, looking into the distribution or cumulative distribution of the weather datasets that we have. Then we select the the month that is varying in a very similar way to the whole dataset, and also 2 months with the maximum difference. One will be the extreme cold months, the other one will be the extreme warm month. Then we select all the typical and extreme cold and warm months, and then we stick them together. Then we will have 3 years. One is typical year, one is extreme cold year, the other one is extreme warm year, as you can see here in this part. So then we use these 3 data sets instead of 390 let's say years of data in our building simulations or energy simulations, and we have assessed results. And for example, here, if you look into the box plot of the results, we got to the, let's say, conclusion that, okay, the distribution or the variations that we are looking for, if we look at these 3 data sets, I mean, typical, extreme cold, and extreme warm is very similar to using all the 390 years. So then we have tried that for different type of energy models or building models, and also for different locations or, on the planet, and results have been satisfactory. So in this presentation, I put all the references, relevant references in this slide. So in the case of interest, you can check them. And as you can see, if we look into the profiles also, which here we have the hourly variations of data sets. And then here, for example, the first one, the one on the top, we are looking into extreme cold conditions, the blue one, and the gray one is all the 290 years. And then here in the middle, we have the typical one, and in the bottom, we have the extreme warm. So by this, we can see that if we use these 3 synthesized or the representative weather data sets, we can, let's say, have a good view of the range of the data and variations. So it also gives us a good, let's say, estimation of the boundaries that we want or we need to design our engineering systems. We also look into indoor thermal comfort. This is from a work that has been submitted, so there is no reference here. For example, here we look into the indoor thermal comfort for the building stock in 4 cities, Barcelona, Madrid, Hamburg, and Munich, for different RCPs. And as you can see, there are differences based on, okay, what RCP do we use, or the locations. So there will be more, hopefully, after having the board accepted. We have also looked into one major risk in buildings in Sweden and many other European countries, which is mold growth. In many buildings, especially in these villas, which have cold attics or unventilated or ventilated attics, but with natural ventilation, we see that mold grows in attics. So, and we did assessment. And we realized that, okay, by climate change in Sweden, especially the southern Sweden, the risk will increase. And we checked different solutions that are available in the market to avoid this mold growth. And we realized that, okay, the only working solution is if we add mechanical ventilation. We have also looked into, for example, the moisture performance or hydrothermal performance of different wall constructions. And we have tried different sets of representative weather data sets, not arranging them based only on representing temperature variations, but also, for example, based on rain variations. And then we have reached to, let's say, different design recommendations and solutions here, especially for retrofitting buildings. One part of our work is looking into urban and microclimates. To do this, we use data from regional climate models, and then we do some urban simulations or urban climate and microclimate simulations. These simulations are mostly CFD simulations, and since these are CFD simulations, they take really long time. So here as well, we cannot run CFD simulations for all the climate data sets that are out. So we had to develop some specific approaches and methods here. So for example, here we look into extreme warm and extreme cold days. For example, we select 3 consequent or 3 to 7 days that are very warm in summer. And then we do CFD simulations for this period. And as you realized in the previous presentation, these thermal shocks, or let's say heat waves, are very important. They can have even casualties. So this is something interesting to look at. And the interesting part is that by changing the design of urban areas or the way we put buildings in an urban area, we usually call it urban morphology. How we design the urban morphology, we can improve urban comfort as well as indoor comfort. So what we want is to try to reach an optimum morphology or optimum design that results in better urban comfort and indoor comfort, and for sure decreasing the energy demand of buildings. We have also looked into urban energy systems. As you can see here, if we have one city or urban area, usually cities are, let's say, a kindly compact concentration of lots of activities. We have many people living in the city, many buildings, different businesses, and there is a huge amount of energy and material transport for one, let's say, limited space or some kind of spatial grid. And for this concentrated area, there is lots of interactions between different sectors, different components, and then the things, or the, let's say, the equations that are running there are becoming very complex. The interactions are very complex then. For example, if we have, let's say, an extreme cold day in Sweden, and it's, for example, raining or snowing, we will get huge increase in energy demand from buildings, while, for example, if it doesn't, if wind doesn't blow, and there is usually not that much solar radiation, then it is really hard to meet the energy demand through renewable generation. So we need to use energy from other sources, while the aim, the long-term aim, is to move more and more towards renewable generation. So for example, in Sweden, the aim is going 100% renewable by 2040, let's say. So, and then it brings huge challenges to design and run energy systems, especially during these extreme conditions. And these extreme conditions put extra cost and load on energy systems. And then we need to invest a lot to make the energy system capable enough to meeting the extreme demand. So we are looking for solutions that enables us to move towards renewable generation while avoiding extra investment or huge investment in increasing the capacity of the energy system. So in this regard, what we do is we add flexibility of the energy system. And then we have defined a term, we call it climate flexibility. It means that when we want to meet the demand during extreme climate conditions, we manage the energy system in the urban area in a way to do not reach an extreme, or let's say a peak load, or to flatten the curve as much as possible by distributing the demand or by, let's say, optimal management of the plant. So then the aim is to increase the climate flexibility, and then this will increase the climate resilience of the energy system. So the energy system doesn't break or can cope with extreme conditions. So, but the challenge is that reaching to such design is very, let's say, demanding, and there are technically no methods that we can use. Actually, we have been quite pioneering here in this regard. We have developed several methods, which one of them, a major one, has been published here, that you have the link. So we use future climate data sets, and then we do two sets of optimization or design for the energy system. We design the energy system for extreme conditions, and we design it also for climate variations. So how we do that? For extreme conditions, we look into extreme hourly conditions in this regard, because our energy system should meet these extreme hourly conditions. Otherwise, it will there will have, for example, there will be, for example, blackouts. So in this regard, we look into these hourly variations. For sure, we cannot consider this variation or this, let's say, blue or red graphs or plots. You cannot consider them as climate because they don't represent the variations of weather. But these are, let's say, the limits that we want to have when we design the energy system. So by looking into extremes, we design or doing robust optimization, we design the energy system in a way to meet the demand or supply the demand during extreme conditions. And then to count for climate variations, we look into different ranges of percentiles. For example, here we have divided the whole range of climate variations per hour into 9 ranges or 9 sequences. For example, the first 5%, then the second 10%, then the third 15%, something like that. Then by this, we do stochastic optimization. Then combination of robust and stochastic optimization will give us a picture, or let's say an optimum energy system or design. So more than that, we also, as I said, we look into climate resilience of energy systems and buildings. So climate resilience is still something very new for us in the field. And we have, let's say, reviewed several works in this regard, but still there are no, let's say, very specific methods that are developed concerning using future climate models and data from, for example, CMIP5 simulations. So still it's, let's say, a field with huge potentials to work. We have suggested, or this is the framework that we apply these days for doing or assessing the climate resilience of energy systems. We use data from climate models, then we generate or synthesize weather data suitable for our energy models, then we run our energy models, and then we assess the resilience. And for resilience, we assess, usually do the assessment based on risk assessment, and then we check the remedies as well. So there are some projects that we are already involved with, and then in this project we use data from Cortex and CMIP5 models. One is a European project, it's an Aeronet project, it is called Flexisync. So in Flexisync, we look into increasing the energy flexibility, and then we want to help the electricity grid and the district heating grid or network. These two should support each other and help each other add to the flexibility, and also we engage these two with buildings. So we want to increase the flexibility in urban areas, and then mainly it's for heating purposes in this project. So we don't look into cooling that much in this project. Another project that we will start soon from June this year is Collective. This project is about using collective intelligence to increase demand flexibility in urban areas, or energy flexibility in urban areas. So we want to design a new, let's say, energy management system. The aim is to have the energy management system in a way that we don't invest a lot on IoT, because many buildings in Europe are old and then the potentials are limited there. So we want to design a simple and quite cheap system that works for many buildings and can be applied easily. And meanwhile, a very important aim or goal that we have is to increase the climate resilience of urban areas. So we want to reach the management system that safely passes the climate shocks. We have some preliminary results in this publication. So we show that, okay, here, for example, we have looked into heating and cooling demand. For heating demand, we compare the system without this new, let's say, demand response system with the one with this collective system. And we show that, okay, the energy demand will decrease considerably if we have this collective system during extreme cold condition, and likewise during extreme warm condition. By having this demand response system, we can decrease the energy demand. More than energy, we are also moving more and more towards other, let's say, systems or infrastructure. For example, looking into water systems, transport systems, or transport infrastructure. So in this regard, recently we submitted one quite large research proposal to a European car, to a Green Deal car. So in this call, we aim at increasing the resilience at the regional scale in Europe. And we have several countries, 8 countries are involved, and we have 4 case studies distributed over different regions in Europe. And then one of the major aims is to use data from Copernicus in, let's say, Cortex, and then use this data in our resilience assessment, and use the data towards improving the resilience of infrastructure in regions over Europe. So thank you very much. In the case of interest, you're very welcome to contact me.